This is the video for Semantics, Distortion, and Style Matter towards Source 3 UDA for Panoramic Segmentation. The first question is why we need panoramic segmentation. Compared to the perspective cameras, which only have 70 degrees, it has omnidirectional scene perception abilities. The pinhole images have limited field of view and do not suffer from the distortion problem. And there existing a lot of label datasets for training neural networks for pinhole image segmentation. But for the panoramic images, they have broader field of view, which is better than the pinhole camera, but it suffers severe distortion problems, and also we do not have a lot of labeled dataset for training. For some privacy and commercial issues, such as the data portability and transmission costs, we do not always have the source data to train the target models in the target image domain. And we summarize the domain gaps between the pinhole and panoramic domains. The first one is the semantic mismatch. The last one is the style discrepancies caused by the distinct camera. Our key idea is to leverage the multi-projection versatility of the panorama data for efficient domain knowledge transfer. And we propose two key modules. The overall framework is shown in figure 2 of our paper. For the panoramic prototype adaptation module, and we apply the tangent projection to transform ERP images into small patches, and also divide in the ERP images into patches with fixed FOV for the knowledge extraction from the source model, which is trained with the pinhole images. And our PPAM possesses 3 distinct characteristics compared to the prior UDA methods for the panoramic images. First, the class-wise prototypes are obtained from the tangent projection and our fixed field of view projection images to alleviate the distortion and semantic mismatch problems. And we also use the global prototypes, and they are iteratively updated with prototypes from the 2 projections during the whole training process. And last, the hard-to-do labels are softened in the high-level feature space with different projections of the same panoramic images. Also, the second module is the CDAM. It imitates the spatial and channel-wise distributions of the dual attention maps between the fake source, also known as the FFP images, and the target ERP data. And the overall training objective is listed in equation 11. We conduct a lot of different experiments to show the effectiveness of our proposed methods, and we first evaluate our methods on the thin pass to dense pass benchmarks, and obviously our methods achieve very high performance, and we can even comparable to the methods which are using the source data. Consistently, our methods also achieve the state-of-the-art performance between all the source-free methods on the cityscapes to dense pass benchmark. And we provide some visualization results on both benchmarks, and our methods achieve the best qualitative results. And we also do the ablation to show that all of the proposed modules and loss functions have a positive impact on improving the panoramic segmentation performance. We also conduct ablation studies to show that the effectiveness of the prototypes in our PPAM module, and all the prototypes from different projections contribute positively to the overall panoramic segmentation performance. And also we investigate the influence of the field of view of FFP images, and the results show that the fixed FOV is the most influential factor in FFP, and using a FOV of 90 degrees achieving the best segmentation performance. And we also give the TSNE visualization to show that our methods can have a better feature distinguishing ability in the high-level feature space.